to all of you guys to this course AVM613, which is analog VLSI circuits. And by the way, a special welcome to all the first year MTech students, MTech VLSI students. So we warmly welcome you to IIST and to our department. And we really hope you have a wonderful time here, the next 2 years of your academic journey here in IIST, and I hope you learn a lot of things which will be helpful in your career. Okay, so welcome all of you guys. And so this course, in case either of the branches are wondering what is happening, who are the other people. So this is a compulsory course for MTech VLSI students, and this is an elective for the final year BTech students. So I know BTech students, some of you might be here to just shop around for the course, see how it is. So I hope you get some idea about what is there in store for you in this particular course today. And just a minute. Yeah, let me start by seeing if there is anyone else who's requesting permissions. Okay, right, no. Right. Let me share my screen. So somebody is recording, right? Okay.
Yes, sir.
Okay. Let me share my screen. Okay, so I hope all of you are able to see the screen that is shared. So first, logistics. As you know, it is timing is the slot C, which means for Wednesday 9 o'clock, 9 to 9:45. Please make sure that you join on time. Being at home, it might be a little difficult for some of you guys to get up on time and so on, but please make sure that you join here on time. Okay. And Thursday 10 o'clock, Friday 11 o'clock. So these three are the slots given for this particular course. All right. And a little more about the logistics. Because it is a combined course, I wanted to create a separate Teams group in Microsoft Teams, so which has been named as AVM613. And I think all of you have been added as members. In case, especially MTech students, in case you haven't found it out, please, I have already added all the MTech students there. But in case you're having any difficulties, let me know. You can just go to your, you can open Microsoft Teams, sign in with your IIST email account, and then you will be able to see all the meetings in the calendar. Okay. And another thing is, please don't start a separate meeting in the Teams. All right. For the classes. So I've already created the meetings for the classes, which is a recurring meeting till December. And just go to your calendar and join in the link. It's very easy for you to join the class. Go to your calendar. I think it will be there in all of your calendars. You can directly click there and join for each of the days. All right. So in case, especially MTech students, you still haven't figured it out, please do let me know. I can help you out and we'll start. Okay, now why this course, or why do we study analog VLSI circuits, right? Now, first of all, one of the major things is that although we use quite a bit of mathematics to understand the subject, but on a regular usage basis, you should be able to quickly look at a circuit and analyze it with very minimal math. Okay, use appropriate approximations and be able to understand circuits. Right. Basically, you need to be able to develop an intuitive feel for circuits. Right. So that is what this course will help you to do. And hopefully, just by looking at a circuit with minimal calculations, you should be able to predict its performance. All right. Now, I also would like to touch upon trying to design these analog circuits in advanced CMOS technology, which includes, things like 16 nanometer FinFET or 14 nanometer FinFET or even lower. Now, these are the contents, and basically we will start with the MOS device and we will go through all these different things. So at the end of the course, you should be able to design an op-amp for any given specification. And we will look at some other circuits like band gap references, output stages. If possible, we'll touch upon active filters. All right. So the prerequisites basically would be that you have a fairly good grasp on network analysis, which is basically your KVL, KCL. Have a good understanding of basic control systems, which is basically poles and zeros, board plots, phase margin, things like that. Right, and also have a good understanding of signals and systems. Basically, if you have a time domain signal, what will it be? What will be in the frequency domain? So I'm not talking about explicitly deriving Fourier transforms or Laplace transforms. I'm not talking about that kind of stuff, but at least an intuitive idea, a basic concept of if you have a sine wave, how does it look in the frequency domain, and things like that. Okay. And of course, basic analog circuits will definitely help you. In this course, we will restrict ourselves to exclusively MOSFETs, okay? Because most of the analog circuits which are being designed now on the IC level is mainly to do with CMOS circuits, okay? All right. Now, the question that many of us might ask is that why look at analog design when we are actually in a digital world, right? Now, the answer is that basically, if you look at any real world signal, the real world signal is essentially an analog signal. Okay. An example could be audio. Like I'm talking to you. My speech is basically an acoustic waveform, right? Like it's basically variation of pressure in air, right? And that is what our eardrums hear, and that's how we speak and communicate. But when we bring in electronics inside, we need to convert this acoustic pressure, acoustic wave, or this air pressure variations to electrical variations. And that electrical signal is basically analog in nature, right? But then you have a lot of digital stuff. So digital electronics especially is very good at processing things, right? Crunching numbers and also storage, right? So, but how do you take an analog real world signal and feed it to a digital system? So you need all the interface electronics which comes in between. So it starts with the sensor, and you have the signal conditioning circuits to work with the sensor. You have filters, you have amplifiers, you have analog to digital converters, and so on. On the other hand, when you want to convert a digital signal to a real world signal, you need to use digital to analog converters, you need to use filters, amplifiers, driver amplifiers, power amplifiers, actuators, all these kinds of things, right? So in this course, we are going to kind of look at the circuits or the building blocks that go into designing these types of circuits, all right? Now, this is something again which I have shown in one of the earlier classes. If you take a typical communication system, a wireless communication system, it can be your mobile phone, it can be your Wi-Fi or a Bluetooth system, whatever it is. If you have a wireless system, this is pretty much kind of what you will have, right? So you have a low noise amplifier, and then you have mixers, you have synthesizers. Now, these blocks we have looked at in the RF integrated circuits course, which was also an elective to the BTech students. For the MTech students, in your next semester, in your second semester, you will be offered an elective, the same elective RF integrated circuits, where you'll have an opportunity to go through the design of all these RF blocks. All right. In this particular course, of course, we will look at the other baseband signal as, right? We can try to touch upon filter design. We can look at variable gain amplifiers, or what goes as the building blocks into these things, right? And if you look at an active filter, if you look at a variable gain amplifier, or even what is going on inside an ADC, so much of it basically revolves around op amps. Okay. Now, when I say op amps, it doesn't mean that we are going to put, of course, a discrete solution can involve an op amp like, let's say, an OP07 or a LM741 or something like that, which you have used in your analog electronics lab. But when I talk about designing an op amp, I'm talking about an op amp which is fully integrated with all the other things. Right? So the op amp that you will design in using MOSFET transistors, which can be fabricated on a chip. Right? So that forms the building block for all these filters and variable gain amplifiers, and even for ADCs. Now, for a transmitter in a modern communication system, it's basically the other way around. You start with a digital to analog converter. You have some good filters, and then of course you have the mixers, synthesizers, pre-drivers, power amplifiers, and so on. Right. So again, the power amplifier, the synthesizer, mixer, this part has been covered or will be covered in the RFIC course in the even semester. But of course, the building blocks for these other things like digital to analog converters and filters and so on will be covered in this particular course. Okay. Now, this is a few years old now, but this is basically taken from the website referenced here at the bottom. So if you open up an iPhone XS, which somebody has done and put it on online, you can basically will just go through all the different ICs that have been used. Okay. To start off with, you have some flash storage, which is obviously a digital IC. This is an Apple audio codec, which is also a digital IC. Then you have a Cypress USB power delivery IC. So power delivery, power related ICs are all purely analog. Okay. So this is an analog IC. You have a display port multiplexer, which is probably digital. You have a battery DC converter, which is again analog. All right. Now, if you go to the other side of the board or underside of the top board, you have this big bionic SoC, which is obviously a digital chip. And then you have an ST microelectronics power management IC, which is obviously a analog IC. You have three audio amplifiers, two for stereo and one for haptics. So these are the three audio amplifier ICs, which are analog ICs again. You have Apple power management IC, that is also analog, right? And then you have another power management IC, which is analog. You have another power management IC, which is analog. You have a battery charger, which is analog. Okay. Now going into your RF board, you see there is a Wi-Fi Bluetooth SoC. Okay. So this is a kind of this is an analog chip, and then this is an analog RF chip. It might also, I think, have some digital components, but I think they are integrating the transceivers. Now, this is an Intel baseband processor or a modem. This is, of course, digital. And then you have an ST microelectronics microcontroller, obviously digital. NFC controller, which is also digital. Wireless charging module from Broadcom, which is again analog RF. Now, the RF board also has certain other components, which is an Avago hybrid band power amplifier, which is again an RF IC or an MMIC. A duplexer, which is an RF component. Power amplifier modules, again an RF IC or an MMIC. You have an RF transceiver here from Intel, which is again an analog RF IC. RF switch, GPS, low noise amplifier, again an RF IC or an MMIC. Power management IC, which is also analog. Okay. Now, in just an iPhone, in one particular phone, which is probably true of most of our phones, you see that you have almost an equal number of analog ICs, or if not, if you combine both analog and RF ICs, it's actually more than the number of digital ICs that you have, right? So analog IC design is actually very crucial, and it is still very important. So if you take any consumer electronic products, if you take, let's say your phones or your laptops or, any kind of a consumer electronic product, you'll see that there is quite a good number of, even if it's a digital heavy product, you will still have some analog components. Okay. To just give you an example, if you take, let's say, your i3 or i5 or i7 processor, which is full digital IC, the digital chip, your processor to work, it still needs a clock, right? Now, clock generation basically is being done using PLLs. Okay. Now, PLL is basically an analog RF block. Okay. So, any digital processor, any microcontroller, any processor that you take will still have some, some analog blocks involved, which is why even digital heavy companies still hire analog engineers. And in fact, if you talk about memories, okay, like let's say SRAM design, DRAM design, or non-volatile memories, any memory design, if you take, the memory readout circuit also is basically a analog and mixed signal circuit. Okay. So which is why memory engineers, if you look at any company like let's say SanDisk or IBM or Intel and all these places, the memory engineers are kind of partly analog engineers basically, right? Because even memory interfaces are analog. You have high-speed IOs, basically the connection between your DDR RAM and your processor, right? When you have multi-gigabit type of link, or rather or even the backplane links in network ICs, right? So when you have like, some 10 gigabits per second link and things like that, now that comes under the purview of mixed signal circuits or analog circuits. In fact, for the MTech VLSI students, we have a separate course in the next semester, which is called as mixed signal VLSI design, where we will go through some of these high-speed I/O designs and so on. Okay, and again, ADC design, D2A design, digital to analog converter design, analog to digital converter design. All these things are basically analog blocks, and this is a very fundamental course which we are going to look at in this semester, which gives you the building blocks and the tools for whatever analog design that you end up doing. Okay. All right. Now, what is analog design? So analog design is not, I would say it's not a purely scientific engineering thing. I would call it as an engineering art. There is a systematic way of designing, right? You do have some mathematical models. You model certain things in a certain way. You use certain approximations and you come up with a design, but also it has an artistic component to it. When I say artistic component, when you have a certain specification, you should learn how to design your system, right? Many times what happens in circuit classes is that there is a lot of focus on analysis. So there is a circuit, you analyze it, you derive equations, you come up with its behavior, but there's very less emphasis on design. But in this particular course, I want to give an equal weightage to design so that you learn how to design circuits, how to design an op-amp, how to design a circuit around an op-amp. What are the constraints? What are the things that you need to take care of? Okay, so that's how this course is going to be, and there will be a lot of simulation exercises and so on. So I will not be focusing entirely on one book, but most of the material can be found in this first book, which is Design of Analog CMOS Integrated Circuits by Behzad Razavi. This is a very standard classic textbook. In fact, talking about classic textbook is the third one, which is the Analysis and Design of Analog Integrated Circuits by Gray and Mayer. Now, this is a very classic book, but the first one is a more updated version. Analog Design Essentials is a very crisp and useful book, but it's quite advanced, and but it's also very nice. It's a very good book. And the CMOS Analog Circuit Design by Alan Hallberg, the fourth one, that is actually a very more of a hands-on kind of a book. You can follow whichever book you're comfortable with. Let me also let me combine it with this. So the evaluation scheme is a little different from the other courses. Okay. So quiz 1 carries 15%, quiz 2 carries 15%. Your internal assessment is a project. All right. So you will be having projects, you will be grouped into teams, and probably you will have a team strength of probably 3. Okay. And you will have to do a project, and that project has the highest weightage in this particular course. As I mentioned, so this is a design heavy, design oriented course, and this is a highly industry oriented course as well. So that those who are seeking for a career in analog design, this is basically your fundamental course. And I want to take it as close as possible to a kind of an industry level where you have to do a design at least till the schematic level and go through its rigorous simulations. Of course, because you're working remotely, we may not be able to do corner analysis and things like that, but at least I want you guys to have a very good hands-on design experience. Okay, so which is why the highest contribution towards your grade will be your project. Okay, and project has to be taken very seriously, and individual contribution should be there. It's not like one person does and two are tagging along. I'll be asking questions individually to each of you guys, and each one has to have designed a particular block, okay, or a sub block. All right. And of course, the final exam carries 30%. Okay. Now, the way in which I'd like to take this course is that there will be quite a few assignments and design exercises and so on, which will be incorporated into your internal assessment. Okay. And because all of you are working, I mean, joining from home, or most of you are joining from your homes, and you don't have access to the simulators that we have in the campus, both because of the limited number of systems and the limited number of licenses. We will be using LT Spice for our simulations. Okay. Soon I will be giving you the model files for 180 nanometer technology node and also a 65 nanometer technology node, and possibly a PTM model for a 60 nanometer FinFET technology as well. Okay. So that you can use these models and you can run your simulations using LT Spice. So if some of you are not familiar with LT Spice, I would recommend that you go through some of the tutorials available online. I think there is also a recorded tutorial, which I think I have done earlier. I'll just find that link and post it in the group so that it will be helpful for those who are new to LT Spice. It's a very intuitive, very easy to use tool. So simulation exercises will be there, and the project also will be done using the same tool. Okay. All right. Now, any questions, any doubts, anything that you would like to ask or comment upon? All right. So, especially with relation to the class link, so all of you have been added to the team. So make sure that you click on, I mean, use your calendar and come to the right link every class. Okay. All right. So let me start off today. We have another 10 minutes for the class to go. Let's start off with the, yeah. All right. So as I mentioned, we'll be designing our circuits using MOSFET transistors, right? So what happens is that if you, yeah, let me. Right. So many of you will be familiar with MOSFETs, I believe. But if not, I will just start with the basic understanding of MOSFETs so that you will be able to, yeah, what is this? Right, okay. You'll be able to understand and kind of freshen up your memory. Okay. Now, when you talk about a MOSFET, so let me just start with a blank slide. So usually for CMOS processes, you start with a typical P minus substrate. Now, what is a P minus? Basically, it is a lightly doped P-type silicon, right? So what is a P-type silicon? It has been doped in such a way that it has some excess of holes, right? Which is the positive charge carrier, right? Now, how do you form your MOSFET? Basically, as the name suggests, it is what is MOSFET? The expansion is metal oxide semiconductor field effect transistor, right? Now, most of you would have learned this in one of the earlier courses. MTech students, you would have come across this in your this one as well, right? In your BTech, right? Now, what does it mean? So basically, it means that there is a metal, there is an oxide, and there is a semiconductor. So this is your semiconductor. So now you have an oxide layer, right? Typically, it can be SiO2 or whatever. So basically, this is your oxide, and then you have a metal, right? Now this forms the gate terminal of your MOSFET, right? Now this alone doesn't form a MOSFET, right? You have two heavily doped regions. Right? This is heavily doped with the N-type dopants, so which is why I'm denoting it as P N plus. So basically, these are your source and drain regions. Correct. So one of them forms, let's say, the drain, the other forms the source. The interesting thing, as we would see, is that the source and drain are interchangeable for a MOSFET. Okay. Now, there is again when we say that this is a metal, so there have been across different technology nodes. So people earlier used metal gates, and then they started using polysilicon gates, polycrystalline silicon gates, and then they've again come back to metal gates. So if you look at different technology nodes, they might have different types of metal, gate material. Okay, some of them will have metal, some of them will have polycrystalline silicon. Okay, so let me just put that polycrystalline silicon. Okay. Now, which is why if you look at layout, typically this is gate is called as poly. All right. So that has kept changing. I think from 28 nanometer onwards, they've gone to metal gates again. Okay. Now, FinFETs also we will look at. Now, FinFETs are such that like you will, okay, we will go into FinFETs little later. All right. Now, this is a diagram that I have taken from one of the books. And this gives you both the perspective view as well as the cross-sectional view of a MOSFET device, right? So as I mentioned, so this is your substrate, P-type substrate, okay? And this is also called as your body or bulk body substrate, whatever it is, okay? Now, typically what happens is all your transistors happen or are formed in the same substrate, okay? So you have one big substrate, imagine a big substrate, and all the transistors are sitting in the same substrate. That's how it happens. All right. Now, this is your drain region, and this is your source region, and also this is your metal, this is your oxide, and your source and drain regions. Now, when we talk about the dimensions of a MOSFET, now we know that this is you would have studied about the W/L ratio of a MOSFET, right? So basically, this dimension, as shown here, this is the width of the MOSFET. Okay, and this dimension is basically the channel length of your MOSFET. Okay, so when we talk about, let's say, a 350 nanometer technology or a 180 nanometer technology or a 65 nanometer technology, 28 nanometer, 16 nanometer, or 7 nanometer, what are we talking about? Basically, we are talking about this channel length. All right. So this channel length is now becoming smaller and smaller and smaller, which is to say that the source and drain regions are coming closer to each other, and the length of the channel across which the electrons have to flow is now becoming smaller and smaller. Okay, so that is your channel length. Now, this is the cross-sectional view that I did it earlier. So the width is basically kind of into the plane of your screen. All right. So I hope you have a clear picture of the MOSFET. Now, I think the BTech students already have taken a course on microelectronics in your 6th semester, where you would have gone through all the fabrication steps and so on. And same with the MTech students, you would have already studied about the fabrication steps and so on in your BTech. You would also have a parallel course which is running, which is on VLSI technology or microsystems and things like that. Okay, so you will go deeper into these things. Once you in those courses, we will not go deeper into device physics beyond this. All right. Now, what happens when you start biasing your transistor? Okay. Now, why is it called as a field effect transistor? Okay. So basically, what happens is this gate material, right? You have a gate electrode or a gate metal. When it is given a certain gate to source voltage, right? Now, what happens is it is going to set up a certain electric field, right? Because there is this oxide here, which is an insulator, there is no direct current flowing like this. There is no current which is flowing like this, right? So it can only exert a certain electric field. Now, based on this electric field, it is going to control the silicon substrate, which is sitting right underneath the oxide. Okay, so now this channel region, this channel L, now what happens as you start increasing this VGS? Okay, so for VGS equal to 0, what do you have? You basically have only the two N plus regions, and this is a P minus substrate. Now we know that for a lightly doped substrate, basically the conductivity is very, very poor, right? And especially when you have, a P minus substrate, let's say you give some drain potential, some source potential, right? Basically, there is going to be a reverse biased diode, which is going to sit like this, okay? Or rather, you want these two diodes which are there to be definitely reverse biased, right? Why should it be reverse biased? Because you don't want current to flow like this from the drain to the substrate, or rather to the bulk terminal. You don't want any current in this one, right? So you want these two diodes, the diode between the substrate and the drain region, the substrate and the source region, both these PN junction diodes to be reverse biased. So how can you reverse bias these two diodes? Can you tell me? So what do you need to do in order to make sure that these things are reverse biased?
Applying the lowest potential to the voltage.
Yeah. So this bulk potential has to be taken to the lowest potential on the chip. Okay. So the bulk or substrate to be connected to the lowest potential on the chip. So typically the lowest potential on the chip is ground. Okay. So typically it is connected to ground. So which is why if you take a MOSFET, right, the bulk will be grounded. All right. Okay. Now we will also see what happens. Okay. Now when your gate voltage is at 0, there is absolutely nothing there. So the current ID is basically 0. All right. Now, as you increase VGS, what happens? Now, there is a positive potential on the gate, right? Now, because of the positive potential and the bulk being grounded, now what will happen? There is no current flow here, and therefore, this particular the region immediately under the oxide is going to attract all the electrons. Correct. So because of the positive potential applied here, slowly more and more electrons are going to get attracted till the point where there is an entire region which is formed here, which is only of electrons. Now, when that happens, it is as if the nature of the substrate is inverted in that particular region. Okay. In other words, there is an inversion layer formed. Why is it called as an inversion layer? Because this is a p-type substrate and it is supposed to have only excess of holes. But because of the potential that you are applying, the electrons are all attracted to the underside of your oxide, right? And so many electrons have been attracted that it literally forms a thin layer underneath the oxide. And now that it forms a thin layer underneath the oxide, that layer has the opposite polarity or the inverse polarity to the rest of your substrate, which is P minus. Now what happens? It is basically like you formed a channel, or rather this is what is called as a inversion channel. Why is it called as a channel? Because this is an N plus region which is rich in excess electrons. Sorry, it's not positive. It's you have excess electrons, right? And you also have a thin channel right under the oxide layer, which is also now having a lot of electrons. Now it is literally forming like one channel between these two regions of N plus regions, right? So this is what is called as inversion layer formation, and the potential at which this inversion layer is effectively formed is what is called as your threshold voltage. Okay, so threshold voltage is the voltage at which an inversion layer is formed. That is, you have sufficient amount of voltage, that is VGS is equal to VTH, such that inversion layer is successfully formed. Right? Okay. Now, still, now that the inversion layer is formed, do you think there will be current flow between the drain and the source? Yes or no?
No, sir.
There is a potential difference.
No. Yeah, why no? Because there is no potential difference between the drain and the source. Okay, an easy way to understand it, it is like saying you have, a bowl of water, and both bowls of water are connected by one pipe in between. Okay, so assume that this is your drain, this is your source, and there is one pipe in between. Like as long as both of them are at the same altitude or at the same height, there is no water flow through the pipe, right? But the moment you kind of raise the drain, right? If suppose you take the drain to a little higher height and you have this channel like this, now obviously you're going to have water flow through the pipe. So this is exactly what is going to happen here. Okay, as long as the source and the drain potentials are the same, there is no current flow. Okay, so in other words, we can say that for VGS less than the threshold voltage, there is no drain current. Okay, this is what is called as the sub-threshold region. Now, again, let me just put an asterisk here and say conditions apply, because in modern silicon processes, what happens is there is what is called a sub-threshold conduction. Okay, so we will see that maybe in tomorrow's class, but the ID is not exactly equal to 0, but definitely ID becomes much smaller. Okay, but in classical square law equation type analysis, we say that the drain current is 0 when the VGS is less than the threshold voltage. Okay. Now for VGS greater than the threshold voltage and VDS equal to 0, again the drain current happens to be 0. Okay. Now for VGS greater than threshold voltage and VDS, that is the drain to source voltage greater than 0, you will have current flow happening. Now, how does the current flow happen and what are the different regions and so on? We will just go through these things. Now, this whatever I took till now is something that you guys will be already familiar with, but I thought I'll just go through it as a refresher so that we'll make sure that all of you are in the same page. Okay. So with this, let me conclude my class today and let's continue in tomorrow's class. So any doubts, any questions?
Sir?
Yeah.
Hello. Sir, if the means that source and drain doping will be different, like one is highly doped and one is slightly doped, then yeah, and the potential are same, they are both ground, then will there be a current?
Okay, so yeah, typically what happens is that you will have both source and drain with the same doping. In any commercial fab, in any commercial, CMOS technology, the source and the drains are equally doped. Basically, what will happen is you might have studied it in the fabrication thing. All these N plus regions will go through the same mask. Okay, so the silicon will have a mask where this region is opened out, this region is opened out, and you have an uniform N plus deposition. Now, probably what you're asking is because of the deposition inaccuracy, maybe there's a slightly higher doping in one side than the other. Is that what you're asking?
Yes, sir. Yes.
Okay. If there's a slight mismatch in the doping and you don't have any potential difference, see, for current to flow, you basically need potential difference, right? Like so, without a potential difference, you literally cannot have the thing. So, although you might have a more excess of electrons on one side, but if there is no potential difference, there is no current flow, right?
Okay.
Sir.
Yeah.
Hello.
Yeah.
Sir, how far we can reduce CMOS scaling? Like the like size of the MOS depends upon, you said, length, channel length and width, right?
Correct.
Like
Correct.
like how far we can reduce channel length? Like can we merge together or we can keep it certain length? What we can do that so we can
Yeah.
get an
So
effective small.
yeah. So if you see when you say 180 nanometer technology node, the minimum channel length that you can put in that particular technology is 180 nanometer. The distance between these two things. Okay. The drawn channel length is 180 nanometer. But if you take it to but in a 180 nanometer technology, you can design a transistor like even in schematics, we will see that when we look at current mirrors and all that, usually we do that. You can increase the channel length, like in an 180 nanometer technology node, like for example, the SEL 180 nanometer, you can have transistors with a channel length of 180 nanometer. You can also have transistors in the same die with channel length of, let's say, 1 micron also, or 2 micron also, or 0.5 micron also. Okay, that is possible. But the smallest length is, limited the lithographic capabilities in that particular foundry, and that happens to be 180 nanometer. The same thing when you talk about, let's say, a 65 nanometer technology node, you will see that the minimum channel length that can be drawn is 60 nanometer. In the same thing, you can go higher also. So in a 65 nanometer technology node, you can have a 180 nanometer channel length device also. Okay, you can design a device with that channel length also. That's not a problem. Okay, but the minimum is 60 nanometer. Now, in absolute terms, how less can we go? That's basically the multi-billion-dollar question that everybody is asking in the world. So you might have seen that IBM has come up, has designed some its processor in 5 nanometer technology, right? And the US government also wanted to establish a big 5 nanometer foundry through TSMC in the US, and that was a big news some months back, right? So I think as of now, what people are kind of headed towards is 5 nanometer. Although I don't think it's very widely commercialized. Most of the latest commercially available ICs might be in the 7 nanometer or 10 nanometer technology nodes, something like that. Or many of them might be in the 16 nanometer, 14 nanometer FinFET technology node. Okay, whether they can go below 5 nanometer, that's what all the industries are breaking their heads over. Okay.
Okay, thank you.
Okay, any other questions? Any doubts?
Sir,
Yeah.
sir, in the iPhone X teardown which you showed, sir, there
Yeah.
we saw a lot of power management ICs. What is the reason for
Right.
high number of power management ICs?
Okay, so power management ICs, basically, so what happens is, let me go to that particular thing. Okay, so for example, if you, yeah. So if you see, for example, if this one, okay, so you have a high mid power amplifier, which is an RF power amplifier from Avago, right? This might have a supply voltage of, let's say, some 5 volt, okay? And your RF transceiver by Intel will be a CMOS IC. This might have a supply voltage of 1 volt or 1.2 volt. Okay, your GPS low noise amplifier also might have a supply voltage of, let's say, 3.3 or 5 volt and so on. Okay, so like that, see, all the digital stuff will pretty much work at like around 1 volt or so. Okay, but some of these other, for example, audio amplifier, this will have a higher supply. Okay, because it has to drive, a speaker and things like that. It will have a higher supply voltage. So for each of the supply voltages, you will have a separate power management IC. Okay. Now, in addition, what happens is, even let's say you take this bionic SoC, which is like the heart of your, iPhone, right? Or for that matter, if you take most of your Android phones, you will have this Qualcomm Snapdragon processor or whatever it is, right? Now, there is what is called as dynamic voltage and frequency scaling. So that's a big term. Just to put it in a very short thing, in digital ICs, power is very much tied to the frequency of operation, right? So if you have a high frequency of, if your clock rate is high, if you're crunching numbers at a higher speed, you will have more power dissipation, because if you talk about an inverter, the power dissipation is what? Alpha times CV squared F, right? So as F increases, which is the frequency of operation, right? Your clock frequency, your power will also increase. Now, suppose you have a low frequency of operation, you can actually operate the chip at a lower voltage, and thereby you will save power. Okay, this is something which is routinely done in all digital ICs, all digital processors. Okay, so because if you look at the power dissipation for a simple inverter, you have C V squared F, right? What is V? V is the supply voltage. So power supply goes as square of the supply voltage. Okay, so if let's say your phone is idle, right? You're not watching a movie or playing your video games or something. So the processor need not work so hard. right? So what they will do is they will bring down the supply voltage from, let's say, 1 volt to something like 0.7 volt or 0.8 volt or something like that. Okay. Now let's say you're playing a very highly computationally intensive game or something. Now what will happen is they will raise the supply to, let's say, 1 volt or 1.1 volt, 1.2 volt, something like that. So in order to raise and lower the supply voltages for all these ICs and also to feed different supply voltages to different ICs from a single battery, you need all these different power management ICs. Does it give you an answer?
Yes, sir. Yes, sir.
Okay.
Sir.
Any other questions? Yes. Yeah. Yeah. Someone had a question. Okay. So if there are no other questions, we can wind up today's class. And thank you guys. So we'll meet. I've already created the links. Use the calendar links to join the classes. All right. Okay. Thanks everyone. Have a
Thank you,
nice
sir.
day.
Thank you, sir.
Thank you. Thank you, sir.
Thank you, sir.